Yeah, hello and welcome to our lecture series on climate protection. First of all, I would like to introduce a rave party taking place today on Landhausplatz. It's organized by the Fridays for Future and it's in favor of wind power. So they have a rave party from Landhausplatz to Sonnendeck. So who is interested to participate after our lectures at 5 p.m. You can join the rave party. Yeah, and now welcome to our lecture series. Our topic today is INNERGY. INNERGY is an acronym of In Valley and Energy. Imagine the year 2040 or 2050 when the whole energy system is completely relying on renewable energy. As a real-world laboratory, the central Inntal region, INNERGY is rehearsing the energy transition. Future situations in the energy system are tested on the current energy grid. I would like to introduce two speakers today. First, my colleague Alexander Thür, working at the Energy Efficient Building Department, and secondly, Martin Lackner from Tirol Kliniken. Alexander Thür is senior scientist. His field of research are system technology for heating and cooling, as well as renewable energies. He will explain you what the Innovation Lab is all about, and afterwards Martin Lackner will speak. He is energy and project manager in the construction and technology department of Tirol Kliniken. His field of research are energy efficiency and project management. Today he will present the energy efficient refurbishment of the AZW building in Innsbruck. Maybe you know the yellow high-rise building close to Freiburger Brücke. This building is also part of the energy project. Welcome, Alexander and Martin.
So, yes, hello from my side also. Thanks for the nice introduction. Then I will start with the Energy Light project. Short introduction, what's about. In Austria, we have about 6 such real-life laboratories. The one, as you can see, I just have to check, yes, I hope you can see the mouse, nice, yes, looks good. So we are the INNERGY project in Tyrol. The other 5 are distributed over the rest of Austria, more or less the eastern part. So there's one in Waldviertel, close to the Czech border. There is one in Burgenland, in Styria. There is one, no, there are 2 in Styria, also Murau and NZ, another one in Lower Austria. It's a so-called flagship initiative, about 100% renewable energy, real laboratories from the ministry, from the BMIMI, now Federal Ministry for Innovation, Mobility and Infrastructure. And the goal of this project is to have to find solutions for 100% renewable energy world. So this means we are not doing any projects about to change, to get rid of the fossil fuels and to install new stuff based on renewables. The main point is to find solutions how to deal with the situation if we have 100% renewables. So what does this mean? Mainly, it's a very strong part of electricity. We change to electricity for mainly for mobility, very strong, but also for heating. Heat pumps is one of the points. And where does this energy come from? In old times, we had electricity power plants which were running and producing electricity exactly at that time when we need them. Now, with the renewables, with photovoltaic, with wind mainly, but also partly with water power, especially at the streams, at rivers, we get the electricity then when the sources are available, when the fuel somehow is available, which means when the sun shines, when the wind is blowing and water is flowing. So we have a completely turned situation, so that we have to deal with the situation that if we get the energy, we have to check how to manage, how to use it. Can we use it directly perfect situation, or do we have to store it? That's why storage, battery, hydropower plants in the Alps are the important topics. As I said, it's just in summary written here. So this is from the ministry, the main points. So the main point is to develop systems which can work under the boundary condition of 100% renewable energy. And the main keywords are by increasing efficiency of the systems, by using synergy between different systems, sector coupling is a keyword, by dramatically increasing possibilities of flexibility. So trying not to use then the energy when I like it, but much more to check, yes, to try to use it then when it's available. And yes, sector coupling mainly between electricity and heat is the important point. So very important is in these projects how the various elements interact. So we have a lot of elements. We have neighborhoods, energy communities, we have grids, we have consumers, we have people acting in the system. And that, I would say, is one of the biggest topics. It's not only if somebody at home is taking a shower at 9 o'clock in the morning or at 6 o'clock in the morning, it's much more in the mind to change the energy system and to adapt the behavior also in the infrastructure. So for architects, for planners, for installers, it's a very important point that they learn how to think in that way that we can work with 100% energy, renewable energy system. This Lab INNERGY, real life laboratory, consists mainly of two sub-projects, sub-organizations. The one is the Innovation Lab, the other one is the flagship project. I'm responsible for the flagship project with my chief, Professor Wolfgang Streicher. Within this, we are leading a system project with 14 project partners and 9 sub-projects I will introduce later. And the other one is INNERGY Innovation Lab. They have 11 co-financing organizations. And the main topic of this innovation lab is to try to get things running. So to make project initiation, to make project development, to support the projects, and to make and to organize knowledge transfer. So based on our activities in the flagship project, trying to get this into the field, let's say to others, that other communities, villages, organizations like building organizations, whatever, take over the ideas, take over our experiences and try to follow and to copy so that in the end we get an avalanche of new developments. Coming back to the flagship project, which is my main topic. So what are the main goals of this flagship project? As I said, we have 6 of these real-life laboratories in Austria, and we are the one which are mainly focusing on heat. That's why district heating, the district heating network is our main topic. So in short way, making the district heating system, which is the backbone of the sector coupling, ready for the future in the context of 100% supply of volatile renewable energy sources. Why district heating system we think is very important? Because one important point is we have to increase our efficiency, which also means recovery, heat recovery, energy recovery. And there's a very clear physical limitation. All electricity we use in the end, it's, I would say 99 point something percent ends up in heat. There's not a lot of different other results. Of course, if some steel I bend, there is some mechanical energy stored, let's say, in the steel then, but the main stuff is ending up in heat. And to get back this heat, for example, in a building, if I have a ventilation system in wintertime and I blow out the hot air into the outside air, then of course this heat is lost. If I have a ventilation system with heat recovery, partly I can get it back. And there we have a lot of processes, especially with IT centers in the moment. Computers need to be cooled. In the moment, all this heat goes into the ambient air, but this could be also used for other purpose. And to get back this heat is more or less only possible on the heat, physically on the with heat to transport, and this means district heating is one of the important tools. Of course, within a building, ventilation with heat recovery can make the heat recovery inside the building. That's a simple task. But between buildings, for example, I need some other tool, and this is the district heating network. So what is the main topic we are doing here? As I said, district heating network is the core part. So we have industrial waste heat we would like to use to have the possibility of recovery. I will show an example. We will have heat production by heat pumps or combined heat and power systems, which can feed into the network on a central place. We manage the heat transfer between all the producers and consumers, mainly with large storages, maybe integrated in the network. But also it's important that we have feed in or offtake by prosumers. So which means that we have one connection where it can be both, it's consuming energy, but it can also feed into the system, depending on the year, maybe on the season, winter, summer, different, but can be also daily different. And we have decentralized buffer systems, which we can use to increase the flexibility. We can also use user behavior. We can change user behavior. We can make flexible space heating demand, especially in buildings, new buildings, passive houses with very good insulation. In principle, it doesn't matter if I have the heating 6 o'clock in the morning with a certain power, or if I shift this for 2 hours and have it 2 hours later, you do not feel it in the building. The air temperature in the building, the room temperature will have almost no influence on that. So this is a lot of possibility we can use for increasing the flexibility. And what is an important point for district heating, reduced return temperature and dynamic district heating temperature spread to increase the efficiency of district heating, to reduce heat losses, but especially to increase the power, because power in a district heating system is flow rate multiplied with temperature difference. And if I have only a small temperature difference, then I need a lot of more flow rate. And if I have a large temperature difference, then the flow rate can be much smaller. Pump electricity is much less, and the pipe dimensions are much smaller, so a lot of advantages. And to find solutions for all of this, we do the research development, also monitoring and evaluation. And this is not only a technical point, it's also a question of legal framework, business models, integration of all stakeholders, as I said in the beginning. So planners, installers, also the owners of the buildings, they need to think in the same way to get good solutions. And then data exchange for energy flow coordination. So IT, digital solutions are also something very important. So here an example, close to Innsbruck network, where we do, for example, simulations, but just again to show the important, to summarize the important points. So to get flexibility, the most important part in the network is a massive reduction of return temperatures, because as I said, then I can increase the power and I can reduce the losses. But this also means I can use decentralized storage systems and building mass activation much more, especially storages. Again, the same. If I have a low return temperature, then I can cool down the storage much more. And in the same volume, I get immediately 30, 40, 50% more heat capacity, which I can use. So demand side control, as I said, is something important. It's not always necessary to heat exactly at the same time because it's cold outside. It can be shifted some hours earlier, some hours later. Central storage is the same as the decentralized storages, and also the network itself can be used. So especially the return pipe as a short time storage. If this is really low temperature, we get into the network, then this can be used more and more also as a short time storage. And this all enables then the possibility to have direct waste heat use at lowest temperatures, which means I have, for example, we have a steel company in the system where, of course, each degree less the return temperature of the network is, desto more heat we can take out. If this is not directly possible anymore, then typically we need heat pumps to take out the waste heat and to lift it to the necessary temperature level. But again, this is if we can reduce the return temperature. This also means we can reduce the flow temperature. And then this is very important for heat pumps. The SPF, the efficiency of a heat pump significantly increases for each degree less temperature it needs to produce. So lower temperature for heat pumps is efficient electricity saving measure. Similar thing, solar thermal systems. So especially with district heating systems, I can make large solar thermal systems in Scandinavia, Denmark, Sweden, also in Germany. A lot of such examples exist, but they're again the same. If they need to produce 90, 100 degree, efficiency is much less compared to 70 or 65 degree. And last but not least, on the electricity side, heat pumps combined from PV or from wind power, we can use and store in the network or in the storages which we have integrated in the network. So it's, again, teamwork is very important, the user behavior, energy flow coordination, and of course also law. So also the right to be allowed to do it. So especially in the electricity sector, we have a lot of changes now. And this is, for example, missing in the district heating sector. We're just waiting for important regulations. Just as an overview, we have 9 sub-projects, which I will briefly introduce with some most important key and highlights. To get an overview, we are placed here in Innsbruck. And if I go to the east side, in Jenbach, fast east, we have INNO T-Next. INNO is producing CHP engines based on gas, natural gas, the old ones, the new ones, hydrogen driven. So this is one of the topics we are working here. Stadtwerke Schwarz, so the utility of the city of Schwarz, they're planning a complete new district heating network. So there, of course, we try from the very beginning to do it best possible. HAL AG, we have here, they have power to heat solutions, which I shortly can show them. Tiroler Rohre, it's a pipe producer, ductile steel pipe producing. So of course they are melting steel, which means a lot of heat, and this waste heat they can send into the network, and that's something we try to make more efficient. IKB, Utility of Innsbruck, they try to use waste heat from the sewage plant with a heat pump. T-Gas T-Next, Fernwärme district heating operator is more or less doing the backbone, is operating all this red line you can see where we have this district heating system. We have IKB again trying to make a demonstration with flexible consumers. We have the university itself, the campus Technik, close to the airport. So there we try to develop a concept where to get rid of our natural gas boiler to have a renewable and flexible heating system. Last but not least, Martin Lackner later on will talk about this HCW building renovation and what they are doing there. So shortly, this backbone TP means Teilprojekt, so sub-project. Fernwärme Innsbruck, district heating system Innsbruck. You see here a little bit more in detail. So all these red lines, this is the district heating network, and we have already quite a lot of industry. For example, here in Wattens, there is natural gas CHP also integrated. We have a biomass boiler here. We have this Tiroler Rohre I mentioned here. We have also already from the sewage plant, there is already some heat going into the system. and so on. And the main point is also, as you can see here, there's a big hole, and this is also part of the project to close this hole to make it more to larger. And one important point is to be able to control it and to optimize such a system. Together with the industry partners, we develop a digital twin to simulate the whole network in all main boundary conditions and to have the KPIs and to do it best possible. So of course, flexibility of storage will be introduced, also consumer, and to use the network as a short storage is a goal to use. And possible chances to integrate large-scale storages. There are some feasibility studies which are done. In Hall, they are quite active already, mainly with power to heat, in combination with a 1,400 cubic meter storage, which is also combined to a biomass combined heat and power plant, which are very efficient, combined with condensation heat pumps. So the flue gas of this biomass heating plant is further cooled down by heat pumps, and so some additional 20% of power they get out. As you can see here, the balancing energy market I got from Hall, this slide. So it's for them in the moment absolutely interesting, and there are quite a lot of other activities in the world also, that if there is a lot of wind and PV power, then also the prices get negative. And so it makes sense to use this electricity, for example, to heat such a storage tank. And by heating this storage tank, you earn money in parallel. So it's perfect business. How does it look like? As you can see it here. So if you pass by train in Hall, you will see this big tower. This is this 1,400 cubic meter. And here you can see this is the, let's say, quite small boiler. It's a 20 megawatt boiler, which is connected to a 10 kilowatt electric grid. Of course, it's higher voltage. And with this, they operate the system. And in summertime, they manage just controlled by the electricity, by this electric boiler to produce all the heat they need for the city. Stadtwerke Schwarz, I have not a lot. They are planning. The planning phase typically takes a long time. It's postponed, and everything takes longer as you wish. But officially, 2 weeks ago, they announced now really in public that this is going to be done. And the main point will be to use groundwater heat pumps, to use wastewater heat pump with the CH plant combined, to use a biomass CHP system and a power to heat system also. And of course, there we try also to develop a flexible control concept, especially in combination with the heat pump, to produce the heat with the heat pump at that time when the electricity price is as low as possible, and to combine this with a heat storage. Another point with IKB, the utility in Innsbruck, and that's one of the core points from my side also, to optimize the technical rooms, the consumers. So in the moment in the networks, we have very typically very high return temperatures, very inefficient. Also the heat losses of networks are very often very high. So very often we have much more than 55-degree return temperature. And also, as you can see it here, the heat substation of district heating to the building is dimensioned 200 to 300% more than it's necessary, which makes it inefficient because the physics does not work, and it makes expensive because for each kilowatt you are connected with, you have to pay. In Austria, something around 20 to 100 euros per kilowatt per year. What is the possibility? So just for example, here what we found out in Hall. As you can see it here, the blue line, that's the return temperature. The two orange lines, this is the, let's say the goal, 50 to 55 degree would be nice. And that's not seldom, that's not the only case. We are around 70 degree here in the return temperature. So you see quite a big potential. The red line is the flow temperature, inlet temperature on the primary side, something around 90 degree. This is fine. But on the green lines here, you see the power on the left axis. The dark green is the 1 hour average, and the thin light green is the 50 minutes value. And as you can see, we are talking about 200 kilowatts here. Here we come a little bit higher, 250 kilowatts installed we have 750 kilowatt. So it's 3 times more. So wasting a lot of money just because of being have too much power. One example, what we propose and we like to demonstrate and to show that, for example, in such a residential building, typically I go back. As you can see it here in the screenshot, what's this existing building? You have the district heating station, you have the buffer storage, and from this buffer storage, in parallel, you deliver the heat to the space heating here and to the hot water preparation. And typically, return temperatures from hot water with circulation line included is very bad, very high, and also quite often, unfortunately, space heating systems have high return temperatures. As you can see here in this diagram on the right side, the violet, this is the original measured system. You see on the x-axis return temperatures weighted by the energy transported. So we can see mainly around 54 degree. We transport here, there's a maximum 17% of the heat all of the year. You see, beside right of 50 degree, it's more or less all of the heat transfer. So quite often we have very often very simple optimization possibilities, just pumps much too high flow rates as a parameter standard setting they have. If you reduce them, we found solutions of 50% reduction is possible, then you can get this distribution of the yellow bars. And if you make a cascade concept where some first systems are installed in Germany, in Rosenheim, Munich, also in France, the principle is that you have the buffer storage and you first make the domestic hot water. You don't care about the high return temperatures because this return temperature then is used by the mixing valve for the space heating system. And in the end, you get back the return temperature of the space heating system, which typically is much lower. And if you make a system like that, then you get the result, the green bars here, you can see we are in total more than 10 degrees in average lower with the temperature. So that's something we are going to test. At the next point, unfortunately, most of the people, I would say 70–80% of the population does not know how a thermostat valve really works. It's very often used just as an on-off valve, and the numbers, as we see here, 1, 2, 3, 4, 5, most people think this is power. If I have 5, then it's a lot of heating power. If it's 1, I have less. In real life, this is temperature. So if I have 3, I have 20 degrees. That's the set temperature. And then the valve itself, it's a controller. It controls the power of the radiator to reach this 20 degrees. So there's absolutely no need to each time to change, to go to 5, to go to 1. And this makes the whole system very unstable and makes big problems. In the end, that's what we have in heating systems very often. Extremely bad situation. We have a lot of power. We have high power boilers, heat pumps, district heating stations. We have high power radiators or floor heating systems, but in the end, we would not need them. And it's like a combination of a sports car with Pfluger for English. Sorry. You see from the farmer this tool. So yes, you can see this car is definitely not the right one to use this tool on the field. So it's much too much power and you cannot really control it. Coming to some others. So AZW building, I will skip. Martin Lackner will talk a lot about this. Campus Technik, so that's the technical campus of our university. As you can see there, we are analyzing the potential of waste heat of the IT cooling and of the laboratories. So our physics department uses a lot of heat, electricity, which in the end ends up in heat. And we try to use this to heat the other buildings directly or via heat pumps. In your sub-project 7 in Jenbach, I showed. So there is the idea to use waste heat from CHP test branches they have in the company. So these are quite big machines. So we are talking about several hundred kilowatts. And so each machine which is produced first is tested and then delivered. So of course they produce a lot of waste heat also. This can be used in the district heating system. And also close to this place, the Aachensee, it's a lake where a water power plant is existing. And this surplus of electricity, which can be used, is used for hydrogen production. And this hydrogen, again, is used by INNO to test the CHP motors and engines driven by hydrogen. Last but not least, producing hydrogen means I need an electrolyzer, which has not that huge efficiency. So there's something like 30–40% heat loss typically, which can be used. If you have a low temperature system, then it could be used directly with something 45 to 50 degree or in combination with a heat pump. So that's what you can see here in phase one. So this is INNO the waste heat from testing the CHP systems, something around 8 megawatts they have at 90 degree. So 5 megawatt station is already installed. And the second phase, what is already installed also is the electrolyzer to produce the hydrogen. And as I said, around 45–55 degree waste heat could be used. This is not installed yet, but hopefully coming in future. And last but not least, using a heat pump system to use heat from the small river, which is passing by, is also planned to be used. Tiroler Rohre, it's a steel company, as I said. So as you can see already here, quite light, quite high temperatures. So they have exhaust gases with something 400 to 500 degree. So this, of course, with a air to water heat exchanger directly can be used to feed into the district heating network. And low temperature heat can be used via absorption heat pump. So with the high temperature, I can power absorption heat pump, which then takes low temperature heat, waste heat at about 40 degree. And with this, it's lifted to something around 85 to 90 degree. And then also this can be used. So also this is quite an interesting concept. Honestly, they have some problems, but this is always if you do something new, and we try to manage them. Last but not least, also we try to have wastewater. So to use, sorry, I just see, I forgot to translate. So the waste heat from the sewage channel. As you can see here, there are some heat exchangers in the channel where the wastewater is flowing into the sewage plant. There are already a heat pump is existing, which is producing heat and sending into the district heating network. And there's the plan to have at the CH plant. It's quite interesting also for me. It was quite new that the water going in the CH plant and all the bacteria produce quite a lot of heat. So the water going out of the CH plant is warmer than coming in. So there's a huge potential to use heat pumps also to make heat recovery with that. These are ideas and plans and under preparation. The project runs 2 years more. We will see what will come out in the end, and maybe I can present it in 2 years, what we really reached and what are our experiences. So I say thank you for your attention from my side. Questions directly or after? You are the organizer.
Direct or urgent questions we can answer them now, or then afterwards we can have a short Q&A session and discussion about the whole project. So are there any direct questions now? Just feel free, raise your hand and I'll come up with the microphone, or in the chat. If somebody has a question, I can read it and ask to Alexander. There's no question at the moment, no problem. Okay, then I would like to welcome Martin Lackner. The floor is yours. It's about the AZW building. Thank you.
So hello, good afternoon. I want to talk about the AZW building, our education for healthcare. The AZW building is one of the 3 Hutter houses. They were built at about 1976 for the Olympic Games in Innsbruck. So they were used before as a living area for the Olympic and afterwards as an educational building and a nursing area. So about the history, as I told, for the Olympic Games, the buildings were built, and beginning at 1990, it was a nursing training school for the Tirol kliniken, and afterwards there were installed the FHG. It was Fachhochschule Gesundheit, and therefore there was a extension of the classrooms in the basement, and yeah, the tower was in the building quality from 1976. Some windows were changed, but not all. They have uncontrolled ventilation through the windows. They have only, I think, about 4 centimeter insulation at the walls and no insulation on the roof. And so it was a very bad thermal quality. So the building is not a small one. It's about 18,000 square meter gross floor area. We have a basement for education. There are about 2,900 students every year and about 5,600 people in training courses with different healthcare facilities. We have 9 floors for offices upwards, and on the top are 2 floors for living for students and so on. And what was our goal? We want to reduce the energy consumption for about 50%. So overall, and to reduce the carbon emissions to at about 95%. So this was our goal, our target, where we want to go. For this, we have a bouquet of measures to come to our target. First of all, we want to change the lighting to LED. It's a very cheap and efficient way to reduce the power consumption. Afterwards, there was the point with the heating. Our hot water system was very inefficient. We have about 60 kilowatt heat load permanent, and this is a huge amount in summer. And yeah, we have at the neighbor ground a deep well. So there was the thought that we can use it for this area. So we have a cool water for cooling and also water for the heat pumps in the winter. This was the main idea. Another point was the climate protection, because we have no recreation area which were shaded. So it's very hot around the building. So there was the idea to bring the energy efficiency and the climate protection together. Another point was the producer and consumer. So prosumer concept from INNERGY was another idea. And the mobility was another part, because we have a lot of students and therefore a lot of bikes parking around the area. And we want a better way, a friendly way, and also a climate friendly mobility at this area. So at this point, we had the thought, what will be if we isolate the building? The windows weren't in this bad quality, so we had a lot of internal load. The first point was reduce the internal load, make a new hot water system. But the thought was, are the people going with us? Because we have a lot of users which know their building, and what will they do if the building isn't working as they want to be? And so the social aspects were, in our interest, a big point. At first, we started cleaning the facade to make the facade very compact. So one point was to put the balconies into the thermal facade or to cut it up. So our ground floor increased for about 15%. Here you see another point, the thermal bridges, they were really very bad. And also we had a problem with the fire protection at the balconies. Furthermore, they weren't safe, so the parapets had to be removed. And so we said, is it possible to put it into the thermal facade so we get a very compact facade and we have less losses? You can see where the balconies were cut, and on the right side the ventilated facade. Why ventilated? Yeah, the facade is more expensive, but you can rebuild the facade afterwards. You can remove the elements, and so you have a circular economy thought in the same project. Why we have there a plaster on the facade? Because it was from the government. So we had to use the same color and the same look as the old buildings in the neighborhood. Here you can see the pipe system, which was new installed, because at the whole renovation, the classrooms were in use. So we can't cut the whole system. So a new heating and cooling pipe system was installed at the facade. Here you can see where the balconies were expanded. They were now in the thermal facade. And on the right side, there was the Dachboden, don't know. The roof truss, yes, which wasn't isolated, and also was a big hole and energy loss. Here you can see our new radiators, which were working on very low temperature and also used as for a smart low cooling, because they have inside small ventilators, and so they can circulate the air and bring the room temperature about 2-3 kelvins down. We installed a new water system, and therefore we used a booster heat pump. The ground temperature will be produced by a normal heat pump, so about 45 degrees, and the boost to the warm water temperature will bring us the booster heat pumps. So we have large buffers on beside to store the water. Here you can see the building service concept. On this side are the deep well system from the neighbor ground, and here is the heat pump, which uses the well water for production of the heat, and this is the booster pump where you can where we increase the temperature for the hot water system. On the right side, you see the installation for the ventilation system for the living rooms. The 2 upper floors got a ventilation system for a higher living quality. First, we thought about a ventilation system in the offices, but we have the problem that there are a very low ceiling height with only 2.2 meters, and this is too less for a good ventilation system. What are our interim results? We were on a good way. Our power consumption got down at about 40%. Our district heating are lower for about 20%, but our heat pump is not finished yet because we have problem with the well. We have to prepare a new deep well, and the cooling is not finished yet. So we have the problem overheating in the offices. And the people are not very amused about this. You know, 27, 28 degrees in the offices is not so good, but there are a lot of aspects. It's not only the cooling, but the big point is the user interaction and also the operator responsibility. And this is very a big point for us, and will also be a big point, I think, for the other projects, because a technician can prepare a system, but the right use of a system should do the user, and if there's a break between, the whole system wouldn't work. So if we have a low solar altitude, so in March or in October, we have heat in the offices because of the sun protection. We have to we have not a very closed system because of the work inspectorate. We had to make a transparent system. So if the sun is very low, the sun comes through the sun protection. And the point is the transparency from the work inspector and the glare protection and also the heat protection. What's the users doing now? They use cardboards to make the glare protection, and this is completely the wrong way. So the thought is to separate the function of the external heat protection, the sun shadow, and another point is the glare protection inside. And this is the point we are working on now. And another point is the automation of this external heat protection, because they forgot a clear automation. The sun protection is about 5 hours in the morning. It's one way going up and going down, and that's all. And if the users use the sun protection or not, isn't controlled. There are no rules, and some do it not. Some open the window in the biggest heat, and afterwards they say it's too hot. So the user have a big attitude, and we have to bring it down. Also a point is the ventilation behavior, because the users left the offices about 4 o'clock p.m., but the sun goes down at about 8 p.m. So the sun came through the window, overheat the room, and in the morning it's about 28 degrees, and the users say it's too hot, we can't work. So in the morning they have to bring the heat outside, open the windows, and this is another thing that they have to learn, because before they had a very poor window quality and uncontrolled ventilation through the window and the wall. So it wasn't a problem. But now they had a good window, and so they see it's too hot, it won't work, and it's a bad renovation in their mind. Another way is free night cooling. At the beginning we said we should use this possibility to bring the temperature down, and during the project is, in my thought, it were forgotten, but now we think about it to bring the temperature down. And there are another problems because of internal rules. They say we have to close all doors in the night, we have to close all windows in the night, and so they can't use the lower temperature in the night to cool down the building. So there are a lot of measures we should use to bring the new building quality to the users. So the user is a very important point to bring the thermal quality down to the floor, to have the efforts that we want to have, because we spend a lot of money and we want a better quality at the end, and not only users who said it doesn't work because it's too hot. So in the autumn, we start with a big info campaign to get the users informed how they can use the window and the sun shadows, and how they should open the doors in the night to bring the temperature down in the building. Another point is to make a user manual for the staff in the building, and the revision of the sun protection and the free night cooling is also a point in this way. So what we have to do, the raising awareness, as I said, optimization of the installed systems, and another technical measures. The awareness is the point the users and also the operator of the building, to make rules which make sense for the building and the user manual, the optimization of the installed system, and also the energy monitoring, that we know afterwards where the energy is going to. What we are now going on is the climate protection theme, like flood protection, because we are besides the IN. And a measures basement is another point, because this project was funded, or is funded, from the Energy and Climate Fund, because it's one of the flagships projects. So we got money to make the whole project a little bit bigger, in the aspect that we include the theme of the mobility from the students, to make monitors for the public transports, and also monitors for further energy monitoring. Furthermore, there are measures to get shaded recreation areas and so on. And finally, the revitalization of the deep well is a big point, to get our heat pumps working in the case that we want to. So, thank you for your attention.
Yeah, thank you, Martin. Yeah, now we can start the Q&A session. You can ask a question, and yeah, there's one up there.
What is deep well revitalization?
Yeah, we have a deep well, and this broken down, a Tiefbrunnen. Der Tiefbrunnen, und der hat die Funktion verloren. Das heißt, wir ziehen Sand und wir müssen den Tiefbrunnen neu bohren.
So the well was blocked with sand, and it has to be reconstructed more or less. That's the way. But then it could work as before.
Yeah, it worked many years ago, but last year we tested if the function is given. We thought, yeah, we clean the deep well and it's working well, but then we saw that it wouldn't go, and so as I know, we had to make a new deep well.
Yeah. Maybe one remark to the overheating. So we see it on the picture there. Before we had some balconies, which are like an overhang, so it blocks the steep inclination of the sun in summertime. And now the glazing is in the front, and there is no sun blocking, no passive sun blocking. So it have to be actively shaded, and that's the reason why there's a big change from before to afterwards. Yeah, that's just
It's a big change. Also, the rooftop wasn't isolated, so in the night the heat was going through the roof, and now we have a pullover. And
yeah, but the effect is not so high. That's the most effect is the solar radiation impacting. Yeah, that's the case. Yeah, other questions? Let's have a look on the online participants. There's no. Yeah, maybe also a question to Alexander Thür. How about the district network? We have seen in the Inntal Valley there were yeah an existing network in Innsbruck, and there are separate ones. So is it always a good idea to interconnect them, or is it also a good idea to have them separately? Where are the advantages for interconnecting them, or are there also advantages for keep them separated? For example, yeah, Bergl, or in the future you can connect the whole Inntal Valley all in one district. Is it good or is it not good?
As you say, advantage, disadvantage. If you have waste heat available on specific places with very high power, then of course you need the consumers to use this heat. This means you need large enough district heating system. If the whole system is small enough, if the heat sources are not too big in terms of power and heat itself, then of course it can be also individual. So there's no must. There's to connect all these different smaller networks to have one large big one. But if the distances are not too long and the heat losses are not then becoming a problem, then I think there's nothing which is against the connection, because then always I have more flexibility, because I can add different prosumers, I can add new customers, I can add new heat sources. If something is built, some industry is starting, for example, or industry is changing their internal heat concept, so that they can find out that they can use something. So, for example, in Völs we have M-Price, which is a supermarket chain. They built a building where they make food production. So of course they have quite some cooling need, and they have quite a lot of waste heat which can be distributed into the district heating network. And things like that, for example, just in Völs itself with a small network, it might be too small to use everything. Otherwise, you can transport it when the gap is closed to Innsbruck, where maybe it's possible to use it. Also, yes, other industry stuff. So I think in general, in this specific situation we have here in Innsbruck, in this network, up to now, about 40% of the heat produced here is done by natural gas boilers. So there is for sure a need to find other sources to be able to be 100% renewable. in future. And from that point, I think it makes sense.
It was pre-calculated that there's not overcompensation of the losses are not higher than the gains by connecting.
I honestly, I did not do the calculations myself, but I strongly hope that this is taken into account. Yes, of course, it doesn't make sense to have too much losses, of course. That's also why we try to start and to introduce solutions to reduce the temperature, especially the return temperature, because then also the flow temperature can be reduced. And this, of course, in summertime, that's definitely a topic because it's just hot water consumption typically. And that's, for example, also why some ideas also are tested and studied. What is coming in the future due to climate change, getting warmer and warmer, so that in summertime maybe with this waste heat from one place, absorption cooling machines can be used to cool buildings, where then more or less you have the heat for free, and to get the cold. So cooling in future for sure will topic be, as we just heard in presentation before, that this also in future will be a topic in standard residential buildings as well. So I know in Hall that's Hall AG, they get questions from building owners that they would be interested in cooling solutions also in combination with district heating, because they would like to have it. Special business companies say they have, if they make they build high quality apartments, then it's becoming more and more a standard that there's a need that it's also possible to offer cooling possibilities, because people do not accept it anymore without. Even so, as Martin Lackner just told us, that quite often it could be possible to avoid cooling if you have the right behavior of the user, but it's not always possible to avoid it. So yeah, especially in office buildings. I think office buildings is definitely a critical point. Residential buildings are less critical, I would say.
Yeah, thank you very much. And thank you very much also for your pictures from the construction side. So for the students, if you are interested more in the building, there we produced a video about the construction and the solutions in more in detail. I will put the video link on OLAT so you can have a look. It's 10 minutes or so, a short documentary about the refurbishment works, and yeah, then you can learn about the development of the refurbishment. Yeah. Okay. Further questions? Doesn't look like. Okay, then I would say thank you very much for the presentations. Thank you for coming. See you next time in the other lecture hall, which is on the opposite side. It's Kleiner Hörsaal, not here in the Audimax. It's in Kleiner Hörsaal next time. That's the last lecture of this summer semester. And I also would like to welcome you in winter semester. It will also be a lecture series with completely new topics. So if you are interested also in this, you are highly welcome. Thank you for coming. Goodbye. And don't forget to the rave party for the for the wind power in Tyrol. Have fun. Goodbye.